Jai Hind, myself Dr. Alok Vardhan. Currently, I am working as an assistant professor in the Department of Mechanical Engineering at Ajay Kumar Garg Engineering College, Ghaziabad. Today, I will discuss one of the important topic of the subject fluid mechanics and fluid machines, and the topic is hydraulic turbines. So, in this lecture, first of all, I will discuss what is hydraulic turbines, then their classifications, then different types of hydraulic turbines, their constructional details and workings like Pelton wheel turbine, Francis turbine and Kaplan turbine. After then, I will discuss what governing of hydraulic turbines. So, first of all, I will discuss what is hydraulic turbines. Now, basically, hydraulic turbines are hydraulic machines which convert the hydraulic energy into mechanical energy, and further this mechanical energy is utilized to propel the generator which produces the electric current. So, we can say that hydraulic turbines are the hydraulic machines which convert hydraulic energy into mechanical energy, and this mechanical energy further converted into electrical energy with the help of generator. Then, what is classification of hydraulic turbines? So, according to the type of energy at inlet, it is classified into impulse turbine like Pelton wheel turbines and reaction turbine like Francis turbine and Kaplan turbine. So, if the energy at inlet is only kinetic energy, then this type of turbine is called impulse turbine, and the examples of impulse turbine are Pelton wheel turbine. But if the energy at the inlet is kinetic energy as well as pressure energy, then this type of turbine is called reaction turbine, and the examples of reaction turbines are Francis turbine and Kaplan turbine. The second classification of hydraulic turbine is according to the direction of flow through runner. So, according to that, turbines are classified into tangential flow turbine, radial flow turbine, axial flow turbine and mixed flow turbine. Means tangential flow turbine means the flow across the tangent of the runner, then this type of turbine is called tangential flow turbine, and the examples of tangential flow turbine is Pelton wheel turbine. If the flow, if the direction of flow is radially to the runner, then this type of turbine is called radial flow turbine, and the examples of radial flow turbine is Francis turbine. Then what is axial flow? If the flow of the turbine is parallel to the direction of the shaft, then this type of turbine is called axial flow turbine, and the examples of axial flow turbine is Kaplan turbine. And what is mixed flow turbine? Means radial in and axial out, then this type of turbine is called mixed flow turbine, and the examples of mixed flow turbine is modern Francis turbine. So, tangential flow turbine examples Pelton wheel turbine, radial flow turbine examples Francis turbine, axial flow turbine examples Kaplan turbine, mixed flow turbine example modern Francis turbine, modern Francis turbines. Then, according to the head at the inlet of the turbine, the turbines are classified into high head turbine, like Pelton wheel turbine, medium head turbine like Francis turbine, and low head turbine means Kaplan turbine. So this is the according to the head at the inlet of the turbine. So we can say that for high head, Pelton wheel turbines are used, whereas for low head, Kaplan turbines are used. According to the specific speed of the turbine, basically the specific speed of the turbine is calculated by this formula, Ns is equal to N under root P upon H, where H के power 5/4, whereas P is shaft power in kilowatt or H is the net head. So if specific speed is low, then this type of turbine is called low specific speed turbine like Pelton wheel turbine. If specific speed is medium, then this turbine is called medium specific speed turbine like Francis turbine. And if specific speed is very high, then this turbine comes under the category of high specific turbine like Kaplan turbine. So we can say that for high head and low specific speed, we can select Pelton wheel turbine. For medium head and medium specific speed, we can select Francis turbine, and for low head and high specific speed, we can select Kaplan turbine. So these are the classification of hydraulic turbines. Now I will discuss one by one construction and detail of Pelton wheel, Francis and Kaplan in subsequent slide. So first of all, I will discuss Pelton wheel turbine. So basically, the Pelton turbine is a type of impulse turbine used for high head, low flow hydropower applications. It converts the energy of high speed water jets into mechanical energy, which can further converted into electricity. So this is the schematic representation of Pelton wheel turbine. In this diagram, there are some main components of Pelton wheel turbines like buckets. This one is buckets. This is runner. This is shaft. This is spear with nozzles. This is penstock. This is brake nozzle. This one brake nozzle, and this complete structure is called casing. So this is the schematic representation of Pelton wheel turbine. Now, what are key components of Pelton wheel turbine? The first one is nozzle and flow regulator. The function of nozzle and flow regulator is it directs high speed water jets at the runner buckets. Then the second component is runner with buckets. It converts jet energy into rotational motion. Then third one is casing. It protects the turbine and contains splashing water. Then last one is brake nozzle. It stops the runner when needed by applying a counter jet. So these are the key components and main components of a Pelton wheel turbine. Now, what is working behind a Pelton wheel turbine? So high pressure, firstly high pressure water from a reservoir या dam through penstock is directed through a nozzle. The nozzle converts the pressure of water into high velocity jets. The water jet strike the specially designed splits bucket mounted on the periphery of the runner. The bucket is split into two halves with a central ridge allowing the jet to be deflected smoothly without any splash. The water jet imparts its momentum to the buckets, causing the runner to rotate. The deflection of water through 160 to 170 degree ensure maximum energy transfer. Then the runner is connected to a shaft that transfer mechanical energy to a generator for electricity production. And lastly, the water, after transferring its energy, it is discharged at atmospheric pressure into the tail rail. This is the complete working behind Pelton wheel turbine. Now I will discuss the second types of turbine, and it is Francis turbine. So what is Francis turbine? So basically Francis turbine is a reaction turbine widely used in hydroelectric power plants for medium to high head and large flow rates. It operates by converting both pressure and kinetic energy of water into mechanical energy to drive the generator, because Francis turbine is one of the type of reaction turbine. So this is the schematic representation of Francis turbine. So in this figure there are some main components of Francis turbine, which are runner, stationary vanes, this one. This is inlet of Francis turbine. This is scroll or volute casing. This is stationary vanes. Then this is adjustable vanes, and this is draft tube and tail race. So this is the main components of Francis turbine. Now I will discuss the functions of their key and main components of Francis turbine. The first one is spiral casing. So in this, the water enters through a spiral casing, which is volute type, which distributes water uniformly around the turbine. Then second one is guide vanes or stationary vanes. These vanes control the flow direction and regulate the water flow rate entering the turbine. Then third one is runner. The runner consists of a series of curved blades. Water flows through these blades, transferring its energy to the runner and causing it to rotate. Then draft tube. The function of draft tube is, it is a pipe of gradually increasing diameter. It reduces the velocity of water, exciting the turbine, and converts kinetic energy into pressure energy, ensuring efficient energy transfer. Then last one is shaft. The shaft transmits the rotational motion of the runner to the generator for electricity production. So these are the key components and their functions. Now I will discuss the working principle behind the Francis turbine. So first of all, water from the reservoir is directed into the turbine through a penstock at high pressure. The spiral or volute casing distribute these water uniformly around the turbine. Then guide vanes adjust the flow and direct water onto the runner beds at an appropriate angle. Then water strikes the runner bed, transferring both kinetic and pressure energy. This causes the runner to rotate, driving the shaft connected to a generator. And finally, water leaves the runner and enters the draft tube, where its velocity is further reduced and it is discharged into the tail rail. So this is the working principle behind the Francis turbine. Now I will discuss about Kaplan turbine. So what is Kaplan turbine? So basically Kaplan turbine is a type of reaction turbine suitable for low head and high flow conditions commonly used in hydroelectric power plants. It is an axial flow turbine. It's meaning that water flows parallel to the axis of rotation. So Kaplan turbine is also one of the example of reaction turbine. This is the schematic representation of Kaplan turbine. Its components are shaft, guide vanes, runner vanes, scroll casing, draft tube, and here tail race. Now, what is the working principle behind the Kaplan turbine? So first of all, before discussing the working principle of Kaplan turbine, I will discuss the key components of Kaplan turbines and their function. So the first component is scroll casing या spiral casing. It distributes water uniformly around the circumference of the turbine. It reduces velocity while maintaining pressure as water flows towards the guide vane. Then second component is guide vanes या stationary vane. Direct the water at the correct angle to the runner blades. Also help in controlling the flow rate and turbine efficiency. Then third one is runner vanes या runner. Convert hydraulic energy into mechanical energy. The water strikes these vanes and causes the runner. Then fourth one is shaft, transmit mechanical energy from the rotating runner to the generator. Then inlet of the runner vanes, entry point of the water into the runner blades after being directed by guide vane. Then outlet of the runner vanes, exit point of the water after energy transfer leading to the draft tube. Then boss, central part of the runner connecting it to the shaft, provides mechanical support and structural integrity. Then last one is draft tube, converts remaining kinetic energy of water into pressure energy and safely discharge water to the tail race. Also allows placement of the turbine above the tail race level without energy losses. So these are the key components and their functions. Then what is the working behind Kaplan turbine? So first of all, water enters through the scroll casing, which directs it towards the guide vanes. Then adjustable guide vanes control the angle and flow of water entering the runner. These guide vanes help optimize performance by adjusting to varying water flow conditions. Then the Kaplan turbine's unique feature is runner. It's runner with adjustable blades. These blades can change their pitch based on flow requirements, making the Kaplan turbine highly efficient across a wide range of flow conditions. And lastly, after passing through the runner, the water exits through the draft tube, which helps recover residual kinetic energy and leads the water to the tail race. So this is the working behind a Kaplan turbine. Now I will discuss one of the important topic, what is governing of turbines. So first of all, I will discuss what is governing, then its methods. So the governing of a turbine is defined as the operation by which the speed of the turbine is kept constant under all conditions of working. Means it is done automatically by means of a governor which regulates the rate of flow through the turbines according to the changing load conditions on the turbine. So basically, governing means we kept the turbine speed constant in respective of the load condition. This is called governing of turbines. So there are different methods for governing of turbine, but in this lecture I will discuss about oil pressure governing. So this is the schematic representation of oil pressure governing of hydraulic turbines. So in this, the components are centrifugal governor, then this is relay a control valve, this is relay cylinder or servo motor, this is sphere with nozzle, this is piston rod of relay cylinder, this is oil sump, oil pump, and this shaft is connected. This is the turbine main shaft which is connected to the shaft of the centrifugal governor. So what is the working of this oil pressure governor? So first of all, the governing of a Pelton turbine is achieved using an oil pressure governor to regulate the water flow based on the load variation. So first, when load decreases, then in this case, the turbine speed increases, causing the centrifugal governor to spin faster. Due to this, flywheel moves upward due to increased centrifugal force, raising the sleeve. This movement adjusts the lever, causing the control valve to close valve V1 and open valve V2. Due to this, pressurized oil flows to the servo motor, moving the piston and sphere to reduce the nozzle flow area. This reduced water flow decreases turbine speed back to the normal condition. And when load increases, then in this condition the turbine speed decreases, slowing the centrifugal governor. Due to this, flywheel moves downward, lowering the sleeve. The lever adjusts the control valve to close valve V2 and open valve V1. Due to this, pressurized oil moves the piston and sphere to increases the nozzle flow area. Then increased water flow raises turbine speed back to the normal. And the system ensures a steady turbine speed by automatically adjusting water flow based on the load changes. So this is all about regarding oil pressure governor. So this is all about for this lecture. Thank you.